Look at the sky. We rely on satellites for global coverage, but they are incredibly expensive to launch and often suffer from high latency. Now look at the ground. Cell towers are fast and reliable, but they are easily blocked by terrain and struggle to reach remote areas. There is a massive, untapped gap between the Earth and space. Today, bridging this gap is one of the biggest challenges in modern telecommunications. This is where high-altitude platform stations, or HAPS, come into play. They act like cell towers in the sky, offering the vast coverage of a satellite with the speed and flexibility of ground networks. They are the missing link in next-generation connectivity. But traditionally, HAPS are complex, multi-million-dollar aerospace systems. What if we combined accessible, low-power radio technology with lightweight aerial platforms to build a low-cost, working prototype of this network? That became the core of my project. Instead of relying on expensive aerospace gear, I set out to build a sustainable, functional network using accessible electronics and resources provided by the Telecommunications Institute. The architecture I designed relies on three main components: 2 aerial nodes and 1 ground station. At the heart of the aerial nodes are ESP32 microcontrollers paired with LoRa modules, powered by lightweight batteries, and fitted with 868 MHz antennas. But to prove that a communication link is actually working, you need to transmit real information. To quantify our success, I integrated temperature and humidity sensors into the payload. These sensors act as the pulse of our network. The 2 flying nodes read the environment in the sky and beam that telemetry down to my ground station, my laptop, allowing me to visualize the data in real time. To validate this network, we simulated a HAPS environment using tethered helium balloons in a controlled setting, acting as a low-altitude platform, or LAP. During testing, the system came alive, streaming live telemetry to the cloud via ThingSpeak. Even in a simulated environment, we encountered real-world challenges. We observed sudden drops in signal strength. Analysis proved this wasn't a hardware failure, but physics. As the platform rotated, the monopole antennas were pushed into their blind spots. Understanding this link between aerial dynamics and RF performance was a key achievement. Ultimately, this project proves that bridging the gap between ground networks and space doesn't require a satellite. Sometimes it only takes a balloon,